Welcome. Welcome to this talk about pressure distribution in free surface flow. My name is Hubert Chanson from the University of Queensland. Let's try to address two key questions. How to predict the pressure distributions in free surface on open channel flow? For example, when would the pressure distribution be hydrostatic? Second question, when would the pressure gradient differ from hydrostatic and why? Let us start with basic fluid statics. The pressure in a fluid at rest is driven by Pascal law, and the pressure gradient is hydrostatic. That is, dP over dz equals minus rho g, where P is the pressure, Z is the vertical elevation positive upward, rho is the fluid density, and g is the gravity acceleration. In turn, the pressure variation with depth is a linear function. In a free surface flow with hydrostatic pressure distribution, as sketched here, the vertical profile of the distribution is a triangle. And when we have a straight invert or channel bed, and the streamlines are parallel to the invert, the pressure gradient along the direction y normal to the invert will be dP over dy equal minus rho g cos theta, where theta is the angle between the channel bed and the horizontal. And in turn, at the bottom of the channel, the invert pressure will be rho gd cos theta. Let us now discuss three situations when the pressure distribution are not hydrostatic, starting with the ondular hydraulic jump, when we are dealing with a horizontal invert. When we have a series of undulations, as illustrated on this photograph on sketch, the pressure gradient is less than hydrostatic beneath the wave crest because of the concave streamlines. And the pressure gradient will be greater than hydrostatic beneath the trough because of the convex streamlines. This video illustrates another form of ondular jump. It is an ondular surge, and in this particular case, an ondular bore. We are seeing here the tidal bore mass carré of the Dordogne River in southwestern France. In June this year, the front of the bore is marked by a series of surfers riding at the leading edge, and behind them, we see a train of secondary waves, also called ondulations, beneath which the vertical profile of the pressure is not hydrostatic because of the presence of wave crest and wave trough. The second situation is a rounded weir crest, with an example on the bottom right of a circular weir crest and its potential flow solution. The streamlines are concave above the weir crest, and in turn, the pressure gradient is less than hydrostatic. The water depth at the crest of the weir is critical, but its value differs from the expression of cubic root of q squared over g, where little q is a unit discharge, expression, cubic root of q squared over g, which is valid only for hydrostatic pressure. On such a circular weir, we can also show, theoretically, that the dimensionless discharge coefficient is greater than unity, unity being the value for a broad-crested weir. And here, we see an illustration of the flow above a circular crested weir. Movie recorded at 120 frames per second, replayed at 30 frames per second. And in this movie, both the streamline and the crest shape are streamlines. And we see nicely the curvature of the streamline as it passes over the weir crest. Third situation, the flip bucket at the toe of a dam spillway, like here the Wavenhoe Dam. On the flip bucket, the water is deflected upward, the streamlines are convex, and the pressure gradient is greater than hydrostatic. In summary, when considering free surface on open channel flow, the pressure is atmospheric at the free surface. And in absence of streamline curvature, the pressure distribution is hydrostatic. And when there are streamline curvature, the pressure gradient will differ from hydrostatic, and this difference is directly linked to the streamline curvature. A number of relevant references with a final photograph of an ondular tidal bar, and in the foreground, the relevant YouTube video movie. Thank you.